Good evening and welcome to everybody. Thank you very much for joining me and Lee and the articulated session for the second time for me. Certainly, many times has it been done by others. Some of you might have met me last week. My name is Richard Bailey. I'm a plumber in Cape Town, and this is new to me in terms of presenting webinars. This is my second one, obviously being module 2. So cut me some slack, please, and just bear with me if I get a little bit tongue-tied or nervous or something like that. But hopefully we'll get through it without too much incident. If there's anybody who's having difficulty hearing me, or if I'm not coming across clearly, or anything else, any other concerns, just please voice those concerns and let us know so that we can sort it out. What I'm going to do is I'm going to switch my webcam on just for a second. There I am. It'll probably take a few seconds to come up to you. That's me. I'm live. I'm not, as Lee said, I'm not generated in some CG land. It's I'm here. And once again, we're going to switch this webcam off to save some bandwidth. Okay. So this evening session is called, let's get into it, it's called the dynamics of hot water within a solar water heating system. So we're going to be looking at the actual behavior of water within a solar system, what it does, what it can do, and you know, the dangers of it and the behavior of it and so on. So let's kick it off. Let me just get the hang of this lot. Okay, so the expected outcomes of this module, in other words, what I'm hoping to get across to you guys this evening is are those couple of points there you can see. Better understanding of the behavior of water within a system. We're going to touch on thermal expansion and the effects of water in general on a plumbing system, what effects it can have on a plumbing system, and then stratification, something which is very often overlooked. Not overlooked in the sense that we don't know, but it's not considered very often. We all know it's there, it exists, and we all know it's there, but sometimes we just sort of gloss over it and decide not to pay it too much attention, and that is a major factor when it comes to the efficiency of a system. What we need, what I would like from you guys to pre-expectations, I would guess you would say, is a basic knowledge of 10254. In fact, not a really basic knowledge, quite an in-depth knowledge. I'm not here to teach you guys how to install geysers. The assumption is that the geyser installation is well known by you guys, and so 10254 is essential. And then basic math skills. That's not for this session, but it will come in later sessions, and very basic. I'm not a rocket scientist myself, but just the basic functions. And then ability to listen. You'll notice that those of you that have done different webinars, each of us have got our own styles. I don't have too much action, I don't think, on the screens. I would much prefer my voice to be heard, and my sort of me to be the vessel of knowledge rather than the screen trying to dictate to it. There are, of course, points and bullet points coming up, which are necessary, but and of course that's for the review as well when you watch it again in a couple of days' time. And then please ask questions. That's what drives me. You know, I mean, I'm sitting here talking to a blank screen and with no feedback. And if there's anything that is unclear or any a part of what we're talking about that you'd like me to repeat or explain, I'm more than happy to be so. And then I put this picture here. As I said last time, I think this is probably a little bit photoshopped, but it illustrates it quite nicely, the passion that this guy's got to get that photograph. He's determined, albeit his equipment and his feet are on fire. He doesn't care. This slide I've added in from the last time. I know that you guys were with me last time. I said I wasn't going to repeat it, but on second thought, I think I better repeat it because there are some new guys here. So this is me. The picture is to show you that I do actually know what an inside of a ceiling looks like. That's my name, Richard Bailey. I did my apprenticeship in Kimberley. and with my practical and theory, my attendance at college, I did in Cape Town at BIFSA and Athlone Tech, and I qualified in '94, and I've been a PERB auditor for about 5 years. So let's look at different...
Great. Richard, can I just quickly interject? There's something I didn't mention to the guys, and just for the guys' knowledge, is that these sessions are, if you're a PRRB plumber trying to go for the solar accreditation, these webinar series are accredited. So what we mean by that is if you complete all 10 of these series and complete the assessment at the end, it will help you that if you approach a training provider, the likes of a Watersmith or a QuickArt, they will give you what we refer to as credits on the theory component, and therefore you only need to carry out the practical side of the solar installation. Sorry, I forgot to mention that. I just wanted to interject and let the guys know on that specific point. So the sessions might, you might think that the tool session is boring, but you need to complete it to get your accreditation. Okay.
Thank you. Thanks very much, Lee. That's the second time you've saved me from forgetting about that. I should have mentioned it as well. In fact, I'll put it into subsequent things, but we'll chat offline about that. Okay, so let's get into this this session. Water quality and water types is the heading, and let's look at hard water and the effects that hard water has on our system. To be honest with you, for many, many years of my career, I didn't really even bother about the difference whether I'm in a hard water area or not. I mean, who cares? I mean, if I put some pipes in your property, if you got hard water, that's your problem. Well, it's not that simple, especially when we're talking about solar, because it does, as we'll see, negatively affect the performance of that solar, and we have the responsibility to make sure that the thing works properly. So hard water is formed when water percolates through limestone or chalk, and calcium or magnesium or both are dissolved in solution and are deposited in the water and dissolved into the water. And apart from just knowing that you're in a hard water area, it is often indicated, and you can tell by the lack of soap suds or soap lathering when you try and lather up soap between your hands. It doesn't really do it so well. It leaves a sort of a scum on top of the water. Then you know you've got hard water, and you need to sort of take other precautions. Interesting thing to note is that it increases, the intensity of the deposit increases with temperature. So the hot water system tends to become bunged up much quicker than the cold system, and of course we're talking about solar, so that gets as hot as it gets in a domestic situation. So it really is a factor when thinking about the design of the system, and it can affect all sorts of things: pumps, electrics, valves, pipes themselves. That sort of faded picture in the background, you can see that is of an actual pipe, and that's a lime scale buildup inside the pipe. I mean, besides the flow rate, all kinds of other issues come from that. Now, in a solar system, what we're most concerned about, of course, is the collectors and the flowing between the collector and the tank, but also, as you'll see later, and in a couple of other, I think the components module, it really can affect the TP valve and place a real sort of a question mark on the safety of a system, can limescale. So how do we combat it? Well, if you want to treat the water before it gets into your property, you can filter it with micro filters, very, very fine filters, and there's two types. It's reverse osmosis and ultrafiltration. Now, I'm not an expert. I do know that both of them rely on extremely fine filters. Effectively, it is a mechanical filter. It's not it's not a UV light or anything like that. It's a mechanical filter of such a scale that it actually filters out the individual particles. But for a solar system, and to combat it and to combat the effects of the negative effects it would have on a solar system, is to install an indirect system. In other words, don't let or don't allow the water, the hard water, to become or to come into contact with the solar collectors, especially the panel, the flat plate collector, because that will calcify up and it's got serious problems. So yeah, hard water, basically, to just touch on that, you identify it, number one. Number two, if you have got hard water and there's no other system in place to filter it out, put in an indirect system, and that'll take care of, as far as it can from your side, it'll take care of it. Let's have a look at thermal expansion. We all know what it is. It's you know, something gets hot, it expands slightly. Check those train tracks. I mean, that's quite an extreme case, and that's why you have all those joints in concrete and that sort of thing. You have those flexible joints. Now, thermal expansion is something that we almost think about when we're putting in solar systems, geysers, because as water heats up, it expands, and that expansion needs to go somewhere. Now, before we go to the next slide, I'd like to ask Lee just to put poll number 1 up very, very quickly for us. I can read it out if you like. Just if you tell me when it's up on the screen.
No problem. Okay, there we go. For the new guys in the room, this is a poll that we bring up. And just, you know, in your own time, select, well, I wouldn't say in your own time, but within the next minute, just read through it. You know, you can take it away. And just choose which one you believe is the best one. Fire away.
Yeah, very, very simple. It's just to get you guys involved a little bit. So if a master box is installed outside a building and as your balancing factor, should you install a shuttle valve at the geyser only, or should you not bother by installing a shuttle valve at the geyser because the master box acts as one, or should you put a shuttle valve as well as a thermal release valve, at least a pressure relief valve component between the shutoff and the tank? A, B, or C?
Yeah, and that's not a spelling error. It's just that we couldn't get all the words in that. So we're up to 33%. Come, guys. Just this is not a trick question. It's just to get an indication of, you know, it's just a thinking out there in the audience. You know, we can't see who's voting here. We can just see the percentage of the people that are voting. So it's not as though we're going to say, hey, you've done it all wrong or whatever it is. So I'm going to leave it for another 15 seconds, Richard. And then I'm going to close the vote. So please, guys, get your votes in. There we go. Right, so I'm going to close it now. We've got 89% of people have voted. So I'm going to close it off there, and let's see what the results are. There we go. I'm sure you can talk to that, Richard.
I actually can't see that.
Okay, right.
Anyway,
so anyway, so the results came back. 13% of the audience said install only the geysers, shut-off valve at the geyser. Okay, 13% install no added shut-off valve at the geyser. Master box has one. Okay. And then the bulk of everybody said install a shut-off valve and additional relief valve at the geyser.
Yeah, that's quite correct. The thing about a shut-off valve at the geyser, now, if you have a master box outside, for example, it is also the relief component of that geyser. And as the geyser expands and everything's hunky-dory, you have the expansion taking place as per normal through the master box, and it drips out there, no problem at all. However, Mrs. Jones has a bit of water hammer or a leak, or she has an over-eager son that is training to be a plumber and he's trying to change a tap washer or something, shuts off the shut-off valve at the geyser. You have now interrupted the pathway of the expansion of the geyser, which is on. Nobody switched the geyser off electrically, and it can't expand, and now you have overpressurization of the system. Likewise, I think you'll see it in other modules, not other modules, I beg your pardon, in other webinars, that SANS 10254 requires that the geyser has a shut-off at the geyser. So that option was also not correct. So yes, you need to install a shut-off at the geyser with a pressure relief component between that shut-off and the geyser. So that, and then that is your proper installation. Okay, let's have
it's one of those contentious issues that are in the industry at the moment for a lot of guys out there at this. And it's just a understanding of this. I mean, a lot of the manufacturers are coming around and voiding their warranties because of that shut-off valve in between. And a lot of people don't understand the reason why that is the case. You know, we can see that the answers coming through here are very similar to the other sessions. Why you don't understand that specific thing. And maybe we should do a specific session just on that specific one. Anyway, be it as it may, back to you, Richard.
Thank you. Okay. So thermal expansion as it relates to geysers is essentially the process of an increase in volume as the water heats. Now, the density of that water actually decreases, and the volume increases, and the molecules kinetic energy increases. Basically, what is happening is that the molecules are moving faster, knocking into each other more vigorously, more violently, and there's an increase of pretty much what you can call empty space between the molecules. So even though it is only an increase of empty space, it's still incompressible. It is very, very strong. You cannot, for all intents and purposes, and what we're dealing with here, you cannot compress it and you cannot contain it. Nothing that we have in a solar system or a domestic tank system can contain expanding water from a temperature point of view. To give you an idea, and when I read this fact, it must have been about 6 years ago that I first found out that about 2 liters of water is displaced by heating a 150 liter geyser from 30 to 60. That is a huge amount of water, and it's a big volume of water that that needs to go somewhere. So obviously, I'm preaching to converted, but obviously your expansion needs to be properly taken care of. Now, it can't go back up through the main supply coming into the geyser for obvious reasons. There are sometimes check valves, shut-off valves, there's other obstructions in between, but mostly because of the fact that the incoming pressure is high anyway, and you have to allow it to go out forwards. An interesting fact is that water is actually one of the very few materials, or very few materials, I suppose you could call it, that experience what they call a negative thermal expansion. It is it's something that at a certain temperature, the colder you make it, the warmer, the bigger it gets. So at 4 degrees Celsius, it is at its densest. You cannot make water denser than it is at 4 degrees Celsius. So if you start dropping it below 4 to 3 to 2, 1, etc., and you start freezing that water, we all know what happens on cliff faces. You know, we've got this erosion happening. I learned it in Standard 8 geography, where you can erode rock by freezing water in crevices. So it's a very strange phenomenon. It has nothing to do with well, in fact it does. It has to do with solar, because as it freezes, of course, it places pressure on the pipes that it's stuck in and can rupture the pipe. So it's a very interesting fact that it is very rare for materials to have a negative thermal expansion, and water is one of them. What are the symptoms of overpressurized systems? So without going through the rigmarole of having to diagnose everything in depth, dripping taps. If a tap is closed off just enough to stop the water, which many people do, and this thing starts overpressurizing, that tap's going to start dripping. Same with the TP valve. TP valve, let's say your PRV, the pressure control valve incoming, is not functioning properly. It's not allowing the expansion drip to take place for some other reason. Your TP valve will start dripping, hopefully. That's its function. And then pressure surges. So when you open a tap and you experience this sudden spurt or burst of excess pressure coming out before it sort of settles down, those are all indicators of overpressurizing systems, and they're not problems in themselves. They're indicators of a deeper problem somewhere else. So what circumstances could result in overpressurization? Well, you have you have a number of control valves that need to take care of it. As I said, the incoming side and the one that is supposed to do it is a PRV. So if that's faulty, if your TMP is faulty, unbalanced systems and cross connections also can cause overpressurization. If you've got a cross connection and you have 1,000 kPa or 800 kPa of cold water all of a sudden rushing into your hot water system, it's going to do that. I'm sorry, I'm just trying to select a laser pointer, but I can't seem to find it. Anyway, that doesn't matter. We'll do it next time. So what is the relationship between temperature and pressure in a system? We've got temperature on the one hand, which can be caused by faulty thermostats, and pressure on the other hand, which can be caused by faulty valves, but they are connected, they're linked, and they can work independently, but they do also work hand in hand. So your liquid, the water is kept liquid by atmospheric pressure, or the pressure exerted on it by whatever is around it. And if that happens to be a tank at 400 kPa, then the gas which wants to escape from the liquid needs to overpower that force which is pressing down on it from the outside. So the higher the pressure onto a body of water, the higher the temperature is that it's going to boil at. And that's just a physical, a fact of science. So in a 400 kPa system, your boiling point, your real boiling point is 145 degrees Celsius, and a 600 kPa is 160 degrees Celsius. Now, what does that mean? That means that theoretically, you can quite easily in your roof have 150 liters of water at 160 degrees Celsius. Now, that is beyond third degree burns. That's death. And the scary thing about it is that you won't even know that it's there unless something happens or it cools down a little bit later, whatever the case may be. But that is a phenomenon that can actually exist in any geyser if the circumstances are correct. Your safety mechanisms break down. We've all seen calcification and limescale buildup within valves. This sort of thing does happen. Just to give an indication and to illustrate it, in Joburg, the guys that are up in Joburg, I think your water boiling point is about 92 degrees Celsius. So down here at sea level, it's 100 degrees Celsius. So it is there is a major difference in terms of temperature at which water boils when you're talking about pressure. And so when we look at overheating of a system, a certain set of circumstances need to sort of come together for it to overheat, and that's not so difficult in the solar system because the sun cannot be turned off. It is out there. You've got a panel absorbing all that heat, and it's got to go somewhere. And this is also where sizing plays a big role. We'll touch on sizing a little bit later in the series. If you've sized the thing correctly, you've got ample space within that geyser to sort of compensate and accept the heat that is being applied to it. So you've got it limits the issue. So as we said earlier, that at about 400 kPa, you still got liquid water at 150 degrees Celsius or thereabouts. Now, what happens if that 400 kPa suddenly becomes 200 kPa or 150 kPa? Now you've got problems, because in order for that to occur, all you need to do is open a big hot tap somewhere. Big 22 millimeter bath tap, pillar type, 22 mil copper pipe all the way from the geyser down to the pillar type bath tap. Open that flat out, and your geyser at 150 degrees Celsius flashes to steam. Now you've got an explosion on your hands. So you can see that, we all read about circumstances that and incidents that happen to somebody else and far away, but it is real and it can happen. And as an indication there, 1700, I beg your pardon, times the factor of 1700 in terms of volume between water and steam, and that'll happen within, you know, a second. Now it just destroys things. So what are the possible causes of overheating? And the biggest thing in a solar system is stagnation. That means that you've got no flow between, or very little flow between the collectors and the tank. How does that happen? Insufficient height on the thermosiphon. So if you've got a thermosiphon system where your collector is flat to your panel, or I've seen a few that in fact the collector, if you were to measure it accurately, it probably comes about halfway up the panel, up the geyser, which of course is not going to work. Or an airlock in the thermosiphon, which would be caused by pipe routing that dips or creates little water traps or air traps, or a backfill of one of the primary flow or return pipes. All of those things will result in stagnation. And you know, you might install a solar system in May and only come across the sort of issues, the stagnation issues, because of the temperatures in September or August. And this is, so I mean, it's 3 or 4 months down the line, and so this is the dangers. And then as summer hits, now you've got serious issues, and that thing starts to overheat, and all kinds of things can happen. In a pumped system, a split system, you can have pump failures. Also, you can have obstruction, any kind of an obstruction in the primary loop, whether it's the flow or return. And so kinked pipes, incorrectly installed valves, limescale buildup, as we've spoken about before, and then lack of cleaning or flushing. And we'll touch on, when we look at the installation, the importance of putting valves in the correct places. One of those valves is a flush valve at the bottom of a flat plate collector, so that you can periodically open it up and get all the sediment down out of the bottom pipe of the flat plate collector, because that just stops your thermosiphon from happening effectively. Temperature sensor failure. This would be primarily on a pumped system, so your pump would not be told to switch on, and it can be as simple as an alarm guy installing an alarm and standing on a sensor wire and severing it. I mean, you could install a perfect system today, and next week you've got a catastrophe on your hands because the sender wire wasn't properly routed. It wasn't tied off to a particular, place or a route where it's out of the way, I mean, people carry stuff into roofs all the time, including us. We bring in a geyser. You put a geyser down on a wire, and then now you've got a catastrophe. So don't let small little things like that, really minor things like that, end up with massive consequences. And then bad design. We spoke about the sizing. If you've got a 150-liter tank with I don't know, 6 square meters of flat plate collector on it, on a beautifully north-facing roof, in the Highveld, you're in trouble. It's not going to work. It's just not going to work. And what happens when something overheats, a system overheats? Now, these pictures you're going to see here, again, not like if you were there last week, I showed a picture of a cylinder which was installed. These are from my archives, which I didn't have to go and dig out 6 years ago. These are all recent happenings in my capacity, and we'll get to that just now. But what happens when the thing overheats? The whole system's lifespan decreases. You're placing stress and strain not only on the tank and the collector, but on all the valves, fittings, and so on and so forth. I mean, yes, they can handle, some of them can handle, we're talking copper pipes that can handle high temperatures, but some of these components, like that plastic valve over there, it's never been designed to handle 130-degree water. With the temperature increase, you've got limescale buildup increases. The rate of limescale buildup increases. So look at that bottom picture. That's a TP port. That small little black dot in the middle is actually the probe of the TP. You'll see the TP just now. that TP from the outside looked perfectly fine. No problem at all. But that thing ain't going nowhere. It's not sensing no temperature. It's not sensing any pressure. And that's why it blew back through this PRV like that. And I was called out at about 2 a.m. One night to this problem. And there was a small child that had gone to the bathroom and opened a tap, and it was a catastrophe. Nobody got hurt, but anyway. But this is just to show you that safety valves do. I mean, not all valves are infallible, and not all systems are infallible. Things go wrong, and we've got to make sure that when they do go wrong, we've catered for it, and we've looked at it, and it's it's handled. As far as is possible. I mean, we can't prevent everything from happening, but these sort of things do happen. And the more that we realize that it is, in fact, a very, very real possibility that as we walk away from a site this evening at 5 o'clock, by 8 o'clock this evening, we could have a catastrophe on our hands because we didn't do this, or I didn't have a TP valve in my toolbox, or shut it down, don't even commission it. This is that TP valve. As you can see, that probe rusted clean off. It's completely closed up with calcification and sediment. As I said, from the outside, it looked perfect. There was no indication that it was a problematic valve, and it was correctly piped out. So we thought everything was hunky-dory. So you do have TP and PRV valve failures as causes of problems, but it's in the minority. So usually they're damaged, or it's a limescale buildup, or it's malicious. We've all seen, well, I've certainly seen TP valve outlets plugged with plugs, or a piece of pipe on there and a cap put on. Same with PRV. I've seen geysers with the PRV outlet plugged with a Connex cap and the TP valve plugged with a cap because it was dripping, and I don't like dripping, so I'll just plug it. And so this, I mean, yeah, just thinking back on that. Okay, so if there's a restriction between the tank and the PRV, and we've spoken about that before, a non-return valve for some other crazy reason, or a shutoff, which is very much more common. And that shutoff, as I say, it's all fine if it's not shut off. But if it's shut off by somebody that doesn't really know what's happening, that's why it's not allowed. Another thing to just note there: if that shutoff, for example, is a tap, in other words, a rough brass stop tap, you've got a plunger. Those plungers are not always well positioned in the spindle, and they can sometimes drop off. So that plunger, if it's installed vertically, it can drop and sit against the seat, and you have pressure coming from the geyser side trying to move backwards through that stop tap. It's actually pressing that plunger down onto the seat even harder. And that in itself, without any interaction between, or without any input from our side, from a human side, that can then act as a non-return valve. And so shutoff valves can really cause problems. And then incorrect banjo valve configuration. Now, when you put in a banjo valve for a retrofit system, you it's always got to go onto the hot outlet port and be used for the hot outlet as well as the TP discharge. So you cannot use it for a TP discharge and your primary return on the primary loop. Why? Because in the event that it does start calcifying and limescale does start occurring within there, because now you've got it in a inverted commas invisible part of the system. You've got a TP discharge, which should never really discharge, and then you've got a flow return coming in there. When that starts to calcify up and the flow rate starts to slow down and the whole system starts to stagnate, you don't know that it's stagnating, number one, and number two, you don't know that that stagnation is actually restricting the function of your TP valve. So if you put the banjo valve in the hot outlet port and you use the second port on that valve to pipe and to supply your hot water to your points, when and if limescale buildup does occur in that valve, you will notice it at the tap. So you open the tap, you say, yesterday I had lekker strong water, Right now, it's half the flow. Tomorrow, it's even less. You call a plumber, Mr. Plumber comes out and says, you got this problem. I can replace the valve. So for that reason, that's where you put a banjo valve. And if it's not put like that, this is a problem that can occur. We've all seen this. I think a lot of these pictures are well, certainly the first one that came up, that one that went through the scaffolding, that was all that myth. It was on Mythbusters. Quite impressive. But yes, it was an experiment and it was taken to the extreme. But this is the facts of life. I mean, look at it at home. I mean, that's 3 rooms and a roof in it, just annihilated. And this is the power of steam. We got 150 liters of water, 200 liters of water, which flashes to steam, and this is really and truly the result. And it's real stuff. I'm not sure if Lee has left and Victoria is with me now. Is that right? If so, Victoria, could we please put up the second poll?
Yeah, I'm here. I will launch your second poll.
Great, thank you.
There we go.
I can't see if it's up. Is it up?
Yes, I will. It's up right now, and then I'll give you the results once it's been closed.
Okay. So the poll, it's simple. The question is, would a split pumped solar system with a collector above the tank be affected by thermosiphon or not? It's simple. Split pumped with your collector above the tank, would that be affected by thermosiphon or not? Is everybody voting?
Yeah, we've had half of the attendees have voted so far.
No, so I've put everybody to sleep. That's not good news.
That's 60%. Maybe it's just a really difficult question.
Maybe my spelling's not so smart. All right,
okay, I'm gonna close it. Yeah, I'm gonna close the poll and I'm sharing it. So 29% of the attendees said that it would be affected by thermosiphon, and 71% of the attendees said it would not be affected.
Okay, that's quite interesting, and I'm very glad about those results, and I'll tell you why. Because I was expecting it to be pretty much split down the middle, which not quite, but it's good enough. And I must admit, I worded it quite strategically and a little bit slyly, because thermosiphon, as we all know, is something that happens in a thermosiphon system, not in a split pumped system. However, the phenomenon of thermosiphon is, and the action of thermosiphon itself can be looked at in forwards motion or reverse motion. Now, what we call reverse thermosiphon is a very, very real phenomenon which occurs in split pumped systems. And yes, we do call it reverse thermosiphon, not thermosiphon. But effectively, it's the same principle. It's the heat exchange from a low position to a high position of water. Hot water will force cooler water back down, and hot water will force its way upwards. Now, in a split system where you've got the tank above the, I beg your pardon, the tank below the collector, the same principle applies. It's this thermosiphon action that causes the reverse to happen, from the heat from the tank to be dispelled and radiated away in the panels. So it effectively is the same thermosiphonic action. So thermosiphon, the point I'm trying to make is thermosiphon will affect every single solar installation. It just affects it. It is a phenomenon that that will occur. Nature insists that it does occur, and science insists that it must occur. So when you install a system, you've got to look at it and say, when this thing starts thermosiphoning, whether it's reverse or forward or what the case may be, will it then still function correctly? Have I put the correct things in place to prevent the thermosiphon from happening or the reverse thermosiphon from happening? So let's have a look at thermosiphon. It is a fundamental principle of solar water heaters. That's, as I've just said, it's a fundamental principle. You cannot get away with it. It will happen, regardless of the configuration. There are different names for it, but it is a phenomenon that cuts across everything. It is a very weak force, so it can't overcome heavy restrictions. It can't overcome spring-loaded non-return valves and that sort of thing. So it's a very weak force that does need to be allowed. If we want it to occur, let me stress that, if it's in a thermosiphon system that we want it to occur, you've got to allow it to occur, and you've got to take away all the restrictions possible. For best results, we say that the bottom of the tank must be 300 mil higher than the top of the panel. Don't look at this picture, because that's not for best results. It's not going to happen so lekker. But it's a nice little simple illustration of thermosiphon. So the tank must be 300 mil above the top of the panel. And what happens in a thermosiphon system where the tank, let's just look at that picture on the right, for example. If you were to have a thermosiphon system set up like that or close to that, let's say that the tank was level with the top of the panel, you could still experience reverse or slight amount of reverse thermosiphon, whereby some of the heat of the geyser actually gets radiated away by the panel. And that is not uncommon even in thermosiphon systems. So if you've got at least 300 mil between your panel and tank, you've negated that possibility. And in water densities, we get back to that again, is the hotter water gets, the less dense it becomes, and so it floats. Effectively, it floats, and because the same amount of water is taking up more space, and if you blow something up, it becomes lighter if it's the same amount of matter inside of it. And that'll always force the cool water back down, and so the cycle continues. So the thermosiphon action is critical in a thermosiphon setup. If you put any kind of obstruction between or on the primary loop between a thermosiphon panel and a tank, you're going to stall that system. Likewise, if any of the pipes that are joining it or connecting it have got backfalls or a dip or are flat for very long distances or any distance at all, really, you're going to stall that system. It needs a kickstart, and once it's rolling, once it's actually flowing, it is quite resilient to interruptions, but it needs to have zero obstruction almost to get rolling. There was something else I wanted to say. Oh yes, just because we know about shut-off valves and where the shut-off valves are required, and we'll get to this later, so don't worry too much about it. But shut-off valves are required between panel and tank on both the flow and the return lines. So now, for a thermosiphon system, if you put a stop tap, a rough brass stop tap on there, what I described a couple of slides ago is exactly the kind of thing that will stall a system as well. So even though it is a stop tap in a fully open position, and even if it's facing the right way, it's too much it's too risky to put in there. It's got to be a full way, a full bore angle, the lever ball valve. So reverse thermosiphon is essentially the same principle. It's exactly the same phenomenon, just on a different. It's a different direction. So where your panels are above the tank, and you haven't put any measure in place to stop the phenomenon from happening, what happens overnight is all the work and effort that your system has put into gaining heat into the cylinder is just dissipated away. It's radiated away, and you've effectively gained nothing. And I've seen many systems where people have said to me, Richard, I can't understand it. I've just spent 30 grand on this thing, and I haven't saved a penny. Nothing is happening. And you look at it, and the guy hasn't put in a proper non-return or whatever the case may be. The measures haven't been put in place. Non-return valves to use here. A lot of people have their own sort of theories, and I know that a lot of people say different things. The thing about non-return valve, it needs to be a spring-loaded non-return valve, because we're talking about a pump with enough force to open that non-return valve properly, and once it's not pumping, we need sufficient force to close it effectively. And once it's closed, it may not then start to reverse thermosiphon. Now, just a note on split systems and pump systems. Even though it's perfectly installed with a non-return valve and a pump, and it all works perfectly for the first year, it's not to say that it's going to continue working. All you need is a little bit of calcification on the seat of that valve, or the washer in that valve to become damaged slightly in some way, and then you have a very slow leak. But that leak, it results in reverse thermosiphon. So in a year's time, you've got a system that was perfect, but now is simply not working, or it's not working well enough. And this is where maintenance comes in and all those sorts of things. Talking about maintenance, you need to be able to, for the reason I've just described, you need to be able to maintain that valve. Flush it out regularly, open it, inspect it, look at it, and if that happens to be on a 38-degree summer's day, you do not want to be draining that geyser in order to get to the valve, because you're going to burn yourself, you're going to burn everybody that's helping you, you're going to melt the geyser tray. So that's why it's got to be installed with 2 shutoffs either side. So it's a simple matter of going to it, shut off, open, look at it, fix, do whatever, goodbye, put in, and goodbye. And that's the story. It's a 15-minute operation instead of a half a day and 6 injuries, you know. So that's, again, we're coming back to the quality of the installation now. Okay, so if you have a thermosiphon system which is it's forced to be installed with less of a height between the tank and the collector, so less than 300 mil, and reverse thermosiphon becomes an issue in that thing. What do? Now, we don't have these valves in this country. I certainly haven't come across them very easily. I have tried to research them, and they're expensive old things, and they are available in other countries. So it's a real dilemma. But in theory, what you should do is use something called the anti-reverse circulation valve. It's a check valve. It's exactly the same as a non-return valve, and you'd use it exactly the same, except the difference is that it is got an extremely low threshold when it comes to opening and closing. So it will open under a condition of like 2 or 3 millibar, and I'm speaking completely off the top of my head. I don't know that as a fact, but I do know that it's a very small pressure that needs to open it. So thermosiphonic action can take place quite easily with that valve in place, and by the same token, it does shut off effectively. So anti-reverse circulation valve, ARCV is what they're called, and I'm hoping that somebody, maybe not in this first thing, but some 2 or 3 courses down the line, somebody's listening to me, and I'll put out a plea, please somebody import that valve, because we need it desperately in this country. Okay, let's move on to stratification. Stratification is not something, as I said a little bit earlier, it's not something that we really pay too much attention to. Certainly in the first 5 or 6 or 10 years even of my career, I don't even think I knew what stratification was. It was never explained to me, it was never taught to me. It's a very important aspect of ensuring that the system is efficient and runs efficiently and delivers the amount of hot water that it says on the box. it's effectively layers of water which build naturally, form based on temperature within a vessel, and it is a barrier between differing temperatures of water. It's a lot smoother than there's no clear lines, but it is certainly the migration of warm water to the top of a tank, and the cooler water slowly settles down to the bottom and gets heated. And it very carefully prevents water from mixing if left alone and if it's handled properly. But it's very easily disrupted. You can disrupt it with one broken baffle. You know, I've been called out to geysers where the guy says to me, this geyser is working perfectly. It has been done working perfectly for 5 years. All of a sudden, we have one shower and it's done. And all it is a little plastic baffle. You replace the baffle and job done. Job's a good one. So it's easily disrupted, and it has a huge effect on the efficiency and effectiveness of the cylinder. So geysers are designed with this in mind. Obviously, they've all got baffles of some way, shape, or description. This isn't a heat pump course, but I'll just say very quickly that a big problem when guys install heat pumps is they don't install a means by which to control the stratification or the disruption of stratification. Some manufacturers want diffuser pipes, other oaks put mixing valves in, and so on. And it is a hang of an important thing to consider. So when you're designing a solar system, you know, you've got to look at the stratification. Will I be disrupting it when this thing switches on, the pump switches on? What's going to happen? Is it going to draw water from the wrong place? Is it pumping water into the wrong place? Is it pumping cold water into the top? Is it pumping hot water into the, etc.? Try and preserve the stratification layers within a cylinder, and it will, the results will speak for themselves. On stratification, it's much more effective on a vertical cylinder than it is on a horizontal cylinder. Why is that? Because the surface area is less on a vertical cylinder. The conduction of heat, or let's say, put it this way, the loss of heat between the hot water and the cold water downwards is much less because there's a much less surface area, and the area for possible turbulence to occur is also much less. So the retention of stratification layers is much better in a vertical tank than it is in a horizontal tank. In a horizontal tank, you've got the whole surface of that thing, and it's like a big old sea. It's waves and I can't think of the word now. What are those spiral things? You know, you've got hell of a lot of disruption happening, and you've got the area for it to occur. So it's where possible, and I know most of our installations, especially thermosiphon ones, they're all horizontal tanks. 80%, 85% of solar installations are horizontal installations, and that's fine. It works perfectly, but it's just an interesting fact to take note of. Is that vertical cylinders are also, they even in their normal sort of, without solar or any other sort of alternative energy input, they are quite a lot more efficient than horizontal cylinders because of this fact, and also because always at the bottom of a cylinder you have a little pocket of water that doesn't really get heated. It's below the element. It's in an odd little place, and in a vertical cylinder that pocket is much smaller than it is in a horizontal cylinder. So in any event, vertical is a lot more efficient than horizontal. And with that, gentlemen, I think we are done. Just in conclusion, and to sum up what we've just had a look at, is remember that water is a dynamic beast. It's not something that is predictable, or it is manageable, but it's not. It's got a mind of its own sometimes, and we need to just cover all the bases, and because otherwise it can be lethal. It really can, and overheating is a big component of that. And we're talking about solar. This is a solar course, so overheating, if it's going to occur in a domestic plumbing environment, it's 9 times out of 10 going to be as a result of a solar system. So you've got to control it. Make sure the valves are in place. That's the next module. We'll go through all the control valves, the safety valves, and be vigilant and mindful of what you're doing. Always think of the next step. Always think 3 steps ahead. What is going to happen to the stratification if I put this pipe here? What's going to happen to the stagnation factor if I do this there, etc., etc., etc. And if we do that, I'm telling you, it's going to be successful. So the next session is the components and tools that we're going to be using, or that is typically used in a solar system, domestic solar system. Lee's touched on it. I'll say it again. It sounds boring, and for those of you who know their stuff, and I'm sure we all do, it might be just a little bit monotonous and repetitive, but it's well worth a look, and it does form part of the greater course. So you know, I'm really hoping to see you guys there next week. We'll have a look at the valves, safety and control valves. We'll have a look at the different types of tanks and the difference between the tanks in terms of normal conventional electric tank or solar tank. Those 2 tanks, I mean. And then the ancillary equipment, whatever is used to supplement and make our lives a little bit easier in the installation, and that sort of thing. So I'm really looking forward to next week, and this is actually getting easier as it goes along. The last week was not so easy. This week was not easy either, but at least we got through it, and I really hope you enjoyed it. And I think we are a little bit over time, but if there are any questions, I don't know if there are any. If any came through, I don't know if I've put all of you to sleep or what the story.
There's not any right now.
Okay, great. I don't know if that's good or bad, actually.
Yeah, maybe you just explain really well.
Well, gentlemen, thank you very much. I'm assuming they are all gentlemen here. And Lady Victoria, thank you so much for the thing. And that's me. I'm signing off.
All right, thank you very much, Richard. And then if everybody could please just answer the survey at the end, and as well as the assessment, and then this video has been recorded, so if you'd like to go back and check anything, you can. Oh, Richard, we just have one question here.
Yes, I'm here.
It's from Dave. He said, what will happen when someone goes away for a week and no one uses water?
Yeah, that's funny enough. I had a situation, well, a query about that just this week. Somebody asked me to install or come and quote to install a solar system, and I said, well, what's the story? We'll have to do a water audit first and blah blah blah. And the guy said, oh no, it's a holiday home. It's only going to be occupied for 2 months out of the year, or 1.5 months. And immediately I said, well, that's a problem. You can't have a solar system because it's just not conducive to the situation. So the answer, Dave, is that it's going to overheat. That's the bottom line. Unless you're going to, and some people do this, they manufacture a cover, and they actually place the cover over the collector out of sheet metal or whatever the case may be. Manufacture some clips and make sure it's on there tightly. And it's quite a common thing to see holiday homes, solar collectors actually physically covered. That's a very, very, very good solution. But of course, it needs the homeowner to buy into it, and you can't have an infirm person or a person who can't get onto a roof. It's not a solution for them. So if it is a problem in terms of irregular overheating, one of the other major factors could be sizing. If the sizing of the tank is not big enough, and we will go into sizing a little bit later on, it's incredible to see how important sizing is. If the tank is big enough, it allows, in inverted commas, space for the solar collector to collect all the heat and store it safely. So the more water you have to absorb all that heat, the better the whole thing functions. Having said that, you can have as big a geyser as you like, but it's not going to store 2 weeks worth of glaring sunshine on a collector. It's gonna overflow, at least overheat. So unfortunately, it's one of those things. There are mechanisms that are aftermarket that one could buy. There's a controller with a function with a dump valve that controls a solenoid valve, so it measures the temperature of the system, and it gets to a certain threshold, and it opens up, and effectively it dumps it before the TP has to start dumping it. So it protects the TP and it protects the system, because the temperature threshold will be a lot lower than your 94 or whatever degrees it is that your TP is. There are other means of controlling overheating as well, some that are not really common in this country. One is a heat dissipator. It looks like a circular fin, sort of a radiator that's installed at the top of the collector, and it simply acts as a radiator, and you have a thermosiphonic flow through it, and that naturally gets rid of excess heat. They're not available here. I certainly haven't seen them. Again, perhaps it's something that we should really look at. Somebody should look at importing. So there are a number of ways that you can do it, Dave, but there are also some circumstances when you look at a situation, you say, well, perhaps this isn't the technology for this house. Like if you're only going to be there for 2 months in a year, unless you can cover that collector somehow, solar's not really worth it.
Okay, so that's all the questions we have. I don't know if there's anything else from your side, Richard.
No, I think I'm done. Just a thank you. I actually forgot to click the last slide. Here it comes. It's just a thank you to say and for joining us, and hopefully we'll see you all there next week, and not only you but your mates. Shout it from the rooftops, talk about it. Thank you very much.
Okay, thank you guys. I hope you enjoy the rest of your evening, and good night.